In this video, we're going to look at the molar enthalpy of reaction and some examples of problems involving molar enthalpy of reaction. So we're going to be using this formula throughout the video. N delta RHM equals negative MC delta T. So in this formula, everything on the left is going to refer to our system, so our chemical reaction, and everything on the right is going to refer to our surroundings, which will typically be water. So N is the moles of reactant, and delta RHM is the molar enthalpy. So the enthalpy change per mole. M is the mass of the surroundings. C is the specific heat capacity of the surroundings. And delta T is the temperature change of the surroundings. Okay, so what is molar enthalpy? We talked about enthalpy, which is the heat energy generated during a reaction. So molar enthalpy is the enthalpy change per mole of a chemical species. The reason that we look at molar enthalpy is that it's a useful comparison factor. So by instead of having our energy in kilojoules, which is very specific to the experimental conditions, having our energy instead in kilojoules per mole allows us to compare between experiments and substances. So we're going to be using kilojoules per mole pretty much exclusively moving forward. So we're going to start with just some examples and we'll look at the various things we can solve for. So what is the molar enthalpy of combustion for octane? If burning 5 grams of octane increases the temperature of 3.5 liters of water by 16.3 degrees Celsius. So we're going to start all of our molar enthalpy problems with a balanced chemical reaction. So octane is C8H18 plus oxygen, and combustion in an open system will create carbon dioxide and water. And the water is going to be vapor. So to balance this, we're going to just throw some coefficients up, and our oxygen will have a coefficient of 25. So we have our balanced reaction now. And so it's important at this point to assign what is our system in the reaction. So our system is going to be the actual chemical reaction, and what is our surroundings? So that's going to be the thing that changes temperature by either absorbing or releasing energy. And the two are equal and opposite. So our system in this case is going to be the octane itself. So that chemical reaction, we have information about octane. Our surroundings are going to be the water. Water is absorbing energy. So we can write down our equation that we had on the first page. So N delta RHM equals negative MC delta T. And we're going to be solving for the molar enthalpy of reaction. So we're solving for this term that's highlighted with the square. So we're just going to kind of define all of the other terms. So N is the number of moles of octane. So the moles of our reactant. Now we need to actually solve for this. So moles is going to equal mass over molar mass. The mass of octane is 5.00 grams, and the molar mass of octane is 114.26 grams per mole. So this gives us 0.0438 moles. So I've written this number down rounded. While you're doing this math, don't round. Input the entire number from your calculator into the next step of the calculation. Okay, so we have N. M is mass of water. And this is going to be 3.50 liters. So a liter is equal to a kilogram. And we can actually leave that in kilograms. That's not a problem. C is going to be the specific heat capacity of water. And because our mass is in kilograms, we're going to use the units kilojoules per kilogram degrees Celsius. And then lastly, delta T, this is the change in temperature of water. And that's going to be 16.3 degrees Celsius. So we're going to be rearranging this equation for the molar enthalpy, and we're going to do that by dividing both sides by N. So our molar enthalpy of reaction is equal to negative mc delta T over N. Now we can just plug in our numbers. So we have 3.5 kilograms times 4.19 kilojoules per kilogram degrees Celsius times 16.3 degrees Celsius, all over 0.0438 moles. And we get a molar enthalpy of negative 5,463 kilojoules per mole. And we can have 3 significant digits, so we're going to write this as negative 5.46 times 10 to the 3 kilojoules per mole. Okay, so example 2, what mass of propane must be burned to heat 900 milliliters of water from 5 degrees to 97 degrees Celsius? The molar enthalpy of combustion of propane is negative 2,220 kilojoules per mole. So we're going to start by writing our balanced reaction, same as last time. So C3H8 is a gas. Combustion, we combine with oxygen to form carbon dioxide and water vapor. We're going to have 3 carbon dioxides, 4 waters, and 5 oxygen. So we have our balanced reaction. And so we're going to start by defining system versus surroundings. So our system in this case, so system equals negative surroundings. Our system is the propane. So our system is always going to be that reaction. And our surroundings are going to be water. 9 times out of 10 in this course, our surroundings will be water. Occasionally, they might be air or water and another substance. So we're going to write our equation down and define some terms, some variables, and delta RHM equals negative MC delta T. So really quickly, you'll notice that there's not actually a mass on this side of the equation. So we are going to do this in 2 steps, and we're going to start by solving for moles, and then after we've solved for moles, we'll then find the mass. So we're going to start by defining our variables. So this is the molar enthalpy of combustion, which is negative 2220 kilojoules per mole. Our mass of water is 900 grams. But because our enthalpy is in kilojoules, we want to get everything in that kind of category. So this is going to be 0.900 kilograms. So 0.9 liters, 0.9 kilograms. C is the specific heat capacity of water. And again, we want that in kilojoules and kilograms. And then lastly, delta T is the change in temperature of water. And that's just going to be in degrees Celsius. And so that's going to be 97 minus 5, which is 92 degrees Celsius. So now we're going to rearrange our equation by dividing both sides by the molar enthalpy to solve for moles. So moles is going to equal negative MC delta T over our molar enthalpy. So that's going to equal negative 0.9 kilograms times 4.19 kilojoules per kilogram degrees Celsius times 92 degrees Celsius, all over negative 2,220 kilojoules per mole. So if you're not sure if you've arranged anything right, you can check the units. So our kilograms will cancel, our kilojoules will cancel, and our degrees Celsius will cancel, leaving us just with moles. So our answer is 0.156 moles. So that's not the end of our question, because we're asked for mass. So we're going to take this answer and we're going to use our formula. Mass equals moles times molar mass to solve for the mass here. So our molar mass of propane is 44.11. So we're going to take 0.156 moles times 44.11 grams per mole. And we're going to get 2 sig digs, 6.9 grams.